Ladies and gentlemen, good morning and welcome to MFTG. Today I would like to share with you some of the recent progress in meaningful type game theory, and that's MFTG. So the agenda now in the next couple of minutes is to describe you a class of MFTG with random number of decision makers and their outcomes. So a couple of years ago, in 2008, we have introduced evolutionary games with random number of interacting players, and this was really a relevant paper at that time. And the idea was to say that the number of players in practical games, in real games that we see in real life, are not necessarily static, are not necessarily the same from one period to another. Some of the agents play a certain number of periods and then leave the game, and some others appear, join the game, and so on. So the number of players with whom you are interacting might evolve over time. Now, we model this through one particular way of modeling it through a stochastic processes, and then we look at the distribution of that stochastic processes, like counting process if you prefer, and then we evaluate the outcomes based on those number of interacting players. So the setup is the following: you have a meaningful type game, means the pair function, the cost function, the utility function are not necessarily of von Neumann type. So we consider not only the expected utility but also as higher order outcomes like variances and so on. And it means that you're in the context of population games with of meaningful type, your pair function depends not only on your own action but also on the distribution of your own action, not only on your own state but also distribution of your own state, and of course other players' actions and the distribution of state and actions from the other player as well. So in that context, we are interested in looking at how the distribution of the random number of players, how does it affect the outcome, in particular the equilibria and the equilibrium pairs. So here are the results. First thing first, when the distribution rate is involved, we have been looking at, for example, particular distribution for the number of agent, interacting agent, active agent, right? So that could follow, for example, a Poisson distribution, and for Poisson distribution case, you could compute the expected values, the variances in a relatively easy way, and then the equilibria, the dependence on the equilibria, depending on the game, of course, might be computed explicitly to see really the impact of the distribution in the outcome. And this was done in a couple of papers, and these are entitled Evolutionary Games with a Random Number of Players. And recently that was extended to meaningful type games with random number of interacting agents. So the second thing is related to the previous lecture. We have been looking at impact of time delay correlated with the number of interacting players. So the number of interacting players is one parameter that you could play to stabilize actually the time delay. So you play on both parameters, number of interacting players at a given time, or the distribution of interacting players to get there with a time delay to get the stability region. And this is really interesting results that we found. So for some particular dynamics, like regular dynamics, when the delay is small enough and the number of interacting players is large enough, you could stabilize the equilibrium strategies that same as the case without delay. Thanks for your attention, thanks for watching, and see you soon on MFTG. Bye.